Download this code from codegive.com, link in the description below. OK, let's dive into the fascinating and sometimes tricky world of race conditions in the context of PWN college and memory manipulation. This tutorial will cover the fundamentals, potential attack vectors, code examples, and mitigation techniques. Introduction. What are race conditions? A race condition occurs when the behavior of a system depends on the unpredictable timing or sequence of events in concurrent execution. Imagine two threads both trying to update the same variable. The final value of the variable will depend on which thread wins the race to write to the memory location last. The result is often unpredictable and can lead to bugs, unexpected program behavior, and, critically, security vulnerabilities. In the context of PWN college and security exploitation, race conditions can be leveraged to bypass security checks, corrupt data, or gain unauthorized access to resources. They exploit the time gap, even a very small one, between when a program intends to do something and when it actually does it. An attacker can squeeze an exploit within that gap. 2. Key concepts and scenarios. Concurrency. Race conditions almost always involve some form of concurrency. This can be through multiple threads within a single process, multiple processes accessing shared resources, or even through interrupt handlers. Shared resources. The vulnerability stems from shared data or resources that are accessed and potentially modified by multiple actors. Timing dependency. The outcome depends on the specific order in which operations are performed. A slight change in timing can completely alter the result. Check then act. A classic race condition pattern involves a program checking a condition, example user has permissions, and then acting based on that condition. An attacker might be able to modify the condition after the check but before the action occurs. Talk to, time of check to time of use. This is a specific type of race condition and is particularly relevant in security. It describes the situation where the state of a resource is checked at one time, time of check, and then that resource is used later, time of use. Between the check and the use, the resource's state might have changed. File systems are a common target of talk-to attacks. 3. Code examples and exploitation. Let's explore some code examples to illustrate race conditions and how they can be exploited. We'll focus on examples in C, as that's a common language for security-sensitive code and systems programming. A simple threaded counter, vulnerable. Explanation. This code creates two threads. Each thread attempts to increment the counter variable a million times. However, the counter ++ operation is not atomic. It's actually a read-modify-write sequence. 1. Read the value of counter. 2. Add 1 to the value. 3. Write the new value back to counter. Race condition. If two threads execute the sequence concurrently, it's possible for both threads to read the same value of counter, increment it, and then both write the same incremented value back. This results in lost updates. Expected result. If there were no race condition, the final counter value should be 2 increments equals 2000000. However, you'll almost certainly see a value less than that, and the value will vary between runs. How to observe the race. Compile and run the code multiple times. Observe the variation in the final counter value. B. Fixed threaded counter, using mutex. Explanation. This version uses a mutex, mutual exclusion lock, to protect the counter variable. Thread_mutex_lock acquires the lock, ensuring that only one thread can access the critical section, the counter ++ line, at a time. Thread_mutex_unlock releases the lock, allowing another thread to acquire it. *y it's fixed *, the mutex provides atomicity. The increment operation becomes effectively indivisible, preventing the race condition. Expected result * the final counter value will consistently be 20000000. See talk to example, file permissions. Vulnerability * the access call checks if the user has write access to the file. If the check fails, as it should initially, the code pauses briefly with sleep 1, and then attempts to open the file for writing and write to it. An attacker could use a separate process, or thread, to change the permissions of the file between the access, check and the open, /write, calls. Exploitation, concept. 1. The program starts, checks if you can write to temp file.txt, you can't. 2. The program pauses for 1 second using sleep, 1. 3. An attacker, simultaneously, uses another process, example a shell script running in a loop, to rapidly change the file permissions using mod plus w temp file.txt. 4. If the attacker manages to change the permissions before the original program calls open, and write, the program will successfully write to the file, even though the initial access, check failed. Attacker code, shell script, example. How to demonstrate the exploit *. 1. Compile the C code, example gcc talkto.co talkto. 2. Create the temp file.txt if it doesn't exist. 3. Run the C code, /talkto. 4. Immediately after running the C code, run the shell script in another terminal, /mod_loop.sh. 5. If the race is won by the attacker, the C program will report that it successfully wrote to the file, even though the initial access check said you didn't have write permissions. 4. Race conditions in memory management, more advanced. Race conditions can also manifest in memory management scenarios, especially when multiple threads or processes are involved in allocating, freeing, or modifying shared memory. These are often more difficult to detect and exploit. A double free asterisk. Vulnerability * both threads attempt to free the same memory location. This is a double free, which can corrupt the heap metadata and potentially lead to arbitrary code execution. Race condition * the order in which the threads execute the free function determines the outcome. If one thread frees the memory first, the second thread will be freeing already freed memory, causing the heap corruption. Difficult to predict * double frees often don't cause immediate crashes. They corrupt the heap, and the effects might be seen later when other memory allocations / deal locations occur. Be use after free *. Vulnerability * 1 thread, free _data, frees the memory pointed to by data. Another thread, write _data, after the memory has been freed, attempts to write to the same memory location. This is a use after free. Race condition * the timing of the threads is critical. We use sleep, 1, in the write _data thread to increase the likelihood that the free _data thread will free the memory before write _data tries to write to it. However, there's still a race, the threads could still execute in the wrong order. Consequences * use after free can lead to arbitrary code execution if the freed memory is reallocated and contains attacker-controlled data. Mitigation techniques. Preventing race conditions requires careful design and coding practices. Here are some common techniques. 1. Synchronization primitives *. Mutexes, mutual exclusion locks as demonstrated in the fixed counter example. Mutexes are used to protect critical sections of code, ensuring that only one thread can access the shared resource at a time. Thread_mutex_lock acquires the lock, and thread_mutex_unlock releases it. Semaphores are more general-purpose synchronization tools. They maintain a counter, and threads can increment, signal, or decrement, wait, on the counter. They can be used for both mutual exclusion and signaling between threads. Condition variables Condition variables are used to signal threads that a certain condition has become true. They are typically used in conjunction with mutexes. A thread acquires the mutex, checks the condition, and if it's not met, it waits on the condition variable. Another thread, when it changes the condition, signals the condition variable, waking up the waiting thread. Atomic operations Modern CPUs provide atomic operations, example atomic increment, atomic compare and swap, that can be used to perform simple operations on shared variables without the need for explicit locking. These operations are guaranteed to be atomic, indivisible. 2 locking strategies granularity consider the granularity of your locks. Fine-grained locking, locking small sections of code, can improve concurrency but increases the overhead of acquiring and releasing locks. Coarse-grained locking, locking large sections of code, reduces locking overhead but can limit concurrency. Lock ordering if you need to acquire multiple locks, always acquire them in the same order. Acquiring locks in different orders can lead to deadlocks, where 2 or more threads are blocked indefinitely, waiting for each other to release locks. Avoid holding locks for long periods. The longer a thread holds a lock, the more it blocks other threads from accessing the shared resource. 3 thread-safe data structures Use thread-safe data structures, example concurrent queues, concurrent hash maps, provided by your language or libraries. These data structures are designed to handle concurrent access safely. 4 design principles minimize shared state reduce the amount of shared data between threads or processes. If data is not shared, there's no need for synchronization. Consider using message passing instead of shared memory in some cases. Immutable data if possible, use immutable data that cannot be changed after it's created. Immutable data is inherently thread safe. Reentrant functions ensure that your functions are reentrant, they can be called from multiple threads without causing problems. Reentrant functions typically avoid using global variables or static variables. 5 Compiler and OS support Some compilers and operating systems provide features to help detect race conditions, example thread sanitizers, lock analysis tools. Use these tools during development and testing. 6 Careful code review Thorough code reviews are essential for identifying potential race conditions. Look for accesses to shared variables without proper synchronization. Pay attention to check-then-act patterns. 7 File system-specific mitigations, talk to. Stat and open together with o_nofollow, the open function provides the o_nofollow flag. This will prevent the program from following symbolic links. Using a stat call before open can then verify that the opened file is the same as the one checked. Open with o_excl if the purpose is to create a file atomically, then opening the file with o_excl provides that. If the file already exists, open will fail. It avoids a race where 2 processes might both think they are creating a new file. 6. PWN college considerations. In the context of PWN college, race conditions can appear in various challenge scenarios. Simulated file systems. Challenges might involve interacting with a simplified file system implementation where you can talk to vulnerabilities to gain unauthorized access or modify protected files. Multi-threaded servers. Server programs with multiple threads processing requests are ripe for race conditions. Exploits might involve corrupting shared data structures or bypassing authentication checks. Kernel modules, advanced. If you're working with kernel modules, race conditions can have system-wide consequences. Exploits might involve gaining root privileges or causing kernel panics. Heap exploitation. As shown in the double free and use after free examples, heap corruption vulnerabilities often involve race conditions when multiple threads are allocating and freeing memory. Tips for finding race conditions. Think about timing. Whenever you see shared resources and concurrency, ask yourself, what happens if threads access this resource in different orders? Look for check then act patterns. These are prime candidates for talk to vulnerabilities. Examine synchronization primitives. Are locks used correctly? Are there any potential deadlocks? Are locks held for too long? Use debugging tools. Thread sanitizers and lock analysis tools can help you detect race conditions. Debugging multi-threaded programs can be challenging, so use logging and debugging techniques carefully. 7. Conclusion. Race conditions are a subtle but dangerous type of vulnerability. Understanding the principles of concurrency, synchronization, and memory management is crucial for writing secure and reliable code. In the context of PWN college and security exploitation, mastering race conditions can open up a wide range of attack vectors. Remember to use mitigation techniques, conduct thorough code reviews, and test your code under concurrent conditions. Good luck, and happy punning.